All right, so let me write the topics that we are discussing today. So we are continuing chapter 2. I'm going to cover a few more topics on electric potential, and then I'm going to move on and talk about the boundary condition and also energy in electrostatics. Okay, so the topics are, I'm going to continue the example we started on Thursday. So that's on electric potential. I will discuss boundary conditions. And work and energy, I'm going to talk about energy of a point charge distribution. As well as continuous charge distribution. All right. Okay, so these are the topics for today. Let's continue the example we've been doing on Thursday last week. And the question was, we have a spherical shell, right, with a surface charge density, uniform surface charge density of sigma. And we were trying to find the potential inside, electric potential inside and outside the spherical shell. Okay, so we did that example once where we integrated the electric field from infinity to the surface of the spherical shell, and then we also continued inside. So that was one approach. That was not too difficult. The thing is that a lot of times we are calculating potential in order to calculate the electric field, not the other way around. So if you know the electric field, there's not much point of calculating potential. Potential is something, a mathematical tool and a physical concept that helps us calculate the electric field and then forces. Okay, so then what we did was we said any charge distribution, the potential can be calculated as an integral. Okay, so the starting point, if you remember, was the electric potential of a point charge. We said that if we have a point charge Q, the electric potential around this at any position R is simply 1 over 4 pi epsilon 0 Q divided by R, and this is the magnitude. And again, I remind you, potential, electric potential is a scalar function. Okay, it's not a vector function. So it's a scalar function, it does not have any direction, and the superposition principle works on electric potential as well. That means if you have more than one single point charge, what you can do is that you can just add up all these electric potential calculated from each of the point charges and just algebraically add them up, okay? If you have discrete charge distribution like point charges, you can do just one sigma, okay? Meaning that if I have like Q1, I have Q2 and so on, what I do is instead of just one single potential, I have a summation of 1 over 4 pi epsilon 0 Qi divided by, here I will change it to Ri, which is the distance vector from the point charge to the position that I'm calculating this, and that's going to tell me the potential, electric potential at position R. So if we have point charge distribution, we can just add them up using a sigma, okay? Of course, if you have limited number of charges, we can say I equals from 1 to n, if n refers to the total number of point charges that we have, okay? So this is for discrete charge distribution where we have many point charges. Okay. The other way is that sometimes we don't have these discrete charges. What if we have continuous charge distribution? Okay. If we have continuous charge distribution, this sigma, this summation can be transferred to the form of an integral, 1 over 4 pi epsilon 0 integral of dq over ri. Okay, so this is just for continuous charge distribution, and this is for discrete charge distribution. So I want everybody to be very comfortable with these sort of changes we do, moving from point charge to the continuous charge, because this is something we do over and over again in electrostatics. Today we're going to do the same thing for work and energy, and also we will do it for magnetic field and the way magnetic field is created from line currents as well. Okay, so is it clear for everyone how we move from a sigma to an integral? It's more or less okay? Okay, sounds good. So anyway, so we had this one, and the idea was that electric potential can be calculated based on an integral of charges divided by the distance separation vectors. Not vector, but the separation distance. Okay. So, and we were doing this for one example that we have continuous uniform charge distribution on a surface of a sphere. Okay, so technically here we have a spherical shell, uniform charge density sigma, and the question was, what is the electric field, the electric potential at a point that is sitting at a distance z from the center of the sphere. Okay, so because here we have only surface charge distribution, the starting point was integrating. So potential at point z is the integral of 4 pi epsilon 0 integral of sigma over separation vector times dA. And this integral runs on the surface of the integral. Okay, so we started from here. We wrote the r separation vector as a function of the polar angle, as a function of the radius of the sphere, and as a function of z. Okay, so we did that. I'm not going to do all those details because it takes time, but I'm going to jump to where we stopped. We calculated Vz is equal to, I go back to my notes, 4 pi epsilon 0 times 2 pi rz, 2 pi r sigma divided by z times r plus z minus r minus z. Okay, so again, as a reminder, r, capital R is the radius of the sphere. Z is the position at which we are calculating the electric potential. Sigma is the uniform surface charge density, and the rest are just constants, 4 pi epsilon 0, 2 pi, and so on. So the square roots we had was a square root of like r plus z to the power of 2, so that's technically an absolute value of r plus z, and here we get absolute value of r minus z. Okay, so these absolute values we need to be a little careful about. Okay, so r is a positive number, right? And z is also a positive number. So the first one is simply just r plus z, it's always positive. Okay, so I'm going to change that to something like this, r plus z. How about r minus z? Is it positive or negative, or it depends? That depends whether you are inside or outside the sphere. Okay, so if you are inside the sphere, z is smaller than r. So this is going to be equal to, so inside, this is r minus z, and outside, this is z minus r, because outside z is larger than r. Okay, so obviously we have these, and then if we have outside, if we are inside, we have R minus Z that cancels out with a Z here, okay, and makes the whole things independent of Z, meaning that the potential inside is a constant. If you are outside, then of course you have Z here, you have Z here, the potential is gonna be dependent on Z, okay? So with that consideration, if we are outside, where Z is greater than 1, the potential is R2 sigma over epsilon Z, and inside, where Z is smaller than R, Vz is R sigma over epsilon 0. This is technically a constant. Okay, so inside the sphere, as we expected, as we did before, the potential, electric potential is a constant. Electric field is 0, electric potential is constant. Okay, so we have this one. Another way of writing this, if you want to write it in a nicer way, you can write both of these two in terms of Q, the total charge on the sphere. Okay, so you know that if the surface charge distribution is uniform sigma, the total charge on this sphere is 4 pi r squared sigma. And if we write this potential in terms of sigma, outside it's going to be 1 over 4 pi epsilon 0 Q divided by Z. And inside it's going to be equal to 1 over 4 pi epsilon 0 Q divided by R. Okay, and this is what we really expected. Outside the spherical shell, the potential should behave very similar to a point charge, and inside the spherical shell, it should be just constant. Okay, sounds good? Yes, everybody is happy?
Yeah.
All right. So yeah, that was it for this example. Do you have any question? Okay. So the next thing I want to do is that I want to plot electric potential as a function of Z, or as a function of distance from the center of the sphere. Okay, so I want to make that plot, and and below that plot, I want to plot electric field as a function of distance. Okay, so I'm going to keep that because that's useful for our next conversation, which is about electric potential, the relationship between charge distribution, electric potential, and electric field. And we're going to discuss the boundary conditions, which is about continuity and discontinuity of the electric potential and electric field. Okay, so the question, very interesting, very important question, is how the electric field behaves when you pass through a surface charge density. Okay, pass through a surface which carries certain charge. And that is interesting because we have discontinuity in electric field in certain direction, which is normal, and we have continuity of electric field and electric potential otherwise. Okay, so let's go back to this relatively simple example, and let's plot what kind of potential and what kind of electric field we are getting out of this. Okay, so for this, I want you guys to help me as well. Okay, I'm going to ask you if I have V electric potential as a function of distance from the center, and here, let's say this is the radius, of the sphere, how should I plot the electric potential? We have two different equations for inside and outside. How does it behave outside the sphere?
Is it exponential decay?
Outside the sphere,
Oh.
it's decreasing, right? It's decreasing as a function of distance. So here, we have a decreasing function, which should be proportional to 1 over r. Okay. Inside, it's a constant, and is exactly equal to the value of the potential right at the boundary. So inside, we have this continuous potential. Okay, so continuous constant, and as soon as you're outside the box, outside the sphere, it's going to drop as a function of 1 over r. Sounds good? Okay, so what is the relationship between electric field and electric potential? Electric field is negative of the gradient of the electric potential, correct? And for these cases that we have complete spherical symmetry, the electric field is, get rid of this. Here, the electric field is negative of dV over dr. Looks good? So, following this, I need a little more space here. So I'm going to write here, electric field is negative of the gradient of electric potential. And in this case, E only has the radial component, which is dV over dr with the negative sign. Okay. So then if I want to continue this, and if I want to plot electric field, of course, the radial component as a function of distance, what do you expect here? Derivative of this with respect to r is 0. Okay, so here we get 0 all the way to this point. And outside of the sphere, we get derivative of this, which is derivative of 1 over r is 1 over r squared. Okay. Derivative of this is negative 1 over r squared. With this negative sign, it becomes positive. So here we get electric field that is dropping like this as a function of 1 over r squared. Okay. So here, right at the boundary, what we have is discontinuity of the electric field. If you are inside this sphere, there is no electric field. As soon as you move tiny bit outside, okay, you have some positive electric field. So here you have this much of discontinuity. Okay, so you have discontinuity in electric field, but no discontinuity in electric potential. Okay, sounds good? Is it clear what we are discussing here? Yes? Okay, good. So I'm going to stop this example and this here, but I'm going to keep this and I'm going to use that in the future conversation, discussion that we have today. Okay, any question on this example?
So for the electric field, it's going to be...
Let me increase the volume a little bit.
Oh, sorry.
Okay, go ahead.
For the electric field, is it going to be, it's just going to be a steeper decay, right, of the electric field
As
to
a
get
function
further?
of radius, yes, it's going to be a steeper decay. In the sense that it's decaying as a function of 1 over r squared.
Gotcha. Thank you.
Cool? Okay. So let me get rid of this if there's no question on this. I don't like this eraser. Okay, so at the beginning of the class today, I said we did that example in two forms. The first form was when we had the electric field and we integrated the electric field to calculate potential. And I said it's not very useful. Okay, so what I want to discuss now is that I want to give you an overall diagram of what we are trying to find in a typical electrostatic problem. Okay, a typical electrostatic problem starts from the fact that, let's say, we are given a specific charge distribution. Okay, so here I'm showing it as a function of rho, but it could also include some sigma and some lambda surface charge density or linear charge density as well. Okay, so what is usually given is the charge distribution. Charge distribution. And what we want from this is we want to move from charge distribution and calculate E, which is the electric field. Okay, so we have a certain charge distribution. Electric charges are distributed, whatever format, and the goal is usually this: calculating electric field that is created by this charge distribution. Okay, and if you have electric field, you can calculate with forces and so on. Okay, so now among the things we discussed so far, mathematically there is a direct way from charge distribution to the electric field, right? And that was integrating the electric field created from any point or from any infinitesimal charge distribution. Okay, so there is a direct way, and that is, I'm going to write that as an integral here. The E is integral of, the E is 1 over 4 pi epsilon 0, the integral of rho over separation vector to the power of 2 r hat d theta. Okay. And this r is unit vector separation. Okay, so here's a direct way. You integrate charge distribution over the distance times the unit vector and do this. Okay, so if we can do this, the problem is solved. That's it. Okay, and we did that for a couple of cases that we had a special symmetry in the problem that we could do this integral. Okay, so this is a good news. There is a direct way. The bad news is that this is only doable, this integral, you can only carry out in very, very special cases that you have symmetry, you have a specific geometry, so that you can actually calculate this. Otherwise, this integral with charge distribution over r squared times r hat, all the time it's going to be difficult, except a few cases, a couple of them I did in class. Okay, so because this is difficult, we use other ways. Okay. And also there is also the other way around for this. If you have the electric field, you can calculate what sort of charge distribution created that electric field. And this way going around is the differential form of the Gauss law, which is the divergence of the electric field is charge distribution over epsilon 0. And at the same time, we know that the curl of the electric field is 0 as well. Okay, so if we have electric field, we can go back and calculate the charge density. Okay, but the typical question in electrostatics is moving from this way to other way. And the difficulty is that this integral is difficult. Okay, so what is electric potential? Electric potential is a way that a lot of times helps us. Okay. We have this electric potential helps us to move from charge distribution to electric potential. Okay, this from charge distribution to electric potential a lot of times is easier, a lot easier than moving from doing this integral. And then from electric potential, you can calculate electric field. Okay. So if you have random charge distribution, how can you calculate electric potential based on charge distribution? That's very similar integral to this, except that we don't have r hat and we don't have all the complication arising from the vector function format of the electric field. And that is V. I hope this is legible for you guys. 1 over 4 pi epsilon 0. The integral of rho d tau over separation vector. Okay. Can you guys read this? Okay.
Yeah, the bottom is the regular R, right?
The bottom is regular, no, it's a distance vector R, a script R.
Oh, good.
And then once you have the electric field, electric potential, you can take the gradient of the electric potential and calculate electric field. Okay, so this way, this is a way to calculate electric field without doing this integral. So the whole idea is giving you guys an overall picture of why we use electric potential, why is that useful, and mathematically what kind of tool that provide us with. Okay. And of course, from all of this point, you can also go backward. If you have electric field, you can calculate electric potential, where V is negative integral of E dot dl. And from electric potential, you can calculate charge density, and that is the Poisson equation, where Laplacian of V is negative of rho over epsilon 0. Sounds good? Any question?
Professor,
Yes.
what is that? Right after V equals minus something, the left-hand side arrow.
This one?
Yeah, right there.
Mhm.
Yeah. Yeah, what
It's
is that?
negative rho over epsilon 0.
Over,
The
okay.
Laplacian of V is negative of rho over epsilon 0. This is the Poisson's equation.
Okay, thank you.
Any more question?
Yeah, this graph is in the book, right?
This graph, yes, is in the book. All right. So a lot of times we calculate electric potential and electric field using the differential format of the Gauss law and Poisson's equation. Okay, so we sometimes look at this, and from the charge distribution, we set up a differential equation that helps us calculate electric field. Or a lot of times we calculate potential first, and from the potential we calculate electric field. And this is, I would put a star on it because this is much more common, okay? And here's the deal. When you set up any differential equation of this form, what you need is the equation, which is provided here and here. We also need certain specific boundary conditions, okay? The solution of this form of the second order differential equation is never unique until you impose the boundary condition. And once you have the boundary condition and equation combined, then the solution is always used, okay? So for that specific boundary condition, let me ask a question. What is boundary condition at all? what is your view of the boundary condition? Let's say specifically in an electrostatic problem. This is all about how the potential, electric potential and electric field behave at certain points in your geometry, okay? And that could be how they define, how they behave at infinity, okay? So you can assume that electric potential at infinity, when you are way far away from your charge distribution, is zero. That's one boundary condition, okay? Or you can also assume, you can also look at the boundary condition right at certain points that you're crossing any surface. Okay, so for that specific problem we had for a spherical shell, the surface of the sphere was a boundary condition, okay? Because you have charge distribution and the way the electric potential and electric field behave defines the solution of the potential and electric field, okay? So what I'm going to continue in the discussion, I'm going to look at the boundary condition. And the most important one is when you have a surface charge, okay, you have a surface charge distribution and you're going to look at how the electric field behaves on two sides of this surface, okay? So for that, let me erase all of this. I'm going to keep this and I'm going to start with a simple figure, looking at the electric field on two sides of a surface charge density. Okay, so let's imagine we have a surface, doesn't necessarily need to be flat, okay? So let me just draw around some random curvature surface here. And let's imagine it has surface charge density of sigma, which does not need to be uniform, okay, for the sake of our discussion. We can keep it general. Okay, now, let's imagine we have electric field, some random electric field, I would say here, E, which is below the surface. And also let's imagine we have certain electric field, E, above the surface, okay? These electric fields could be created by all other random charge distribution in the whole space, okay? But because we have this surface here, there will be very specific sort of relationship between the electric field below and above the surface. And by that, I mean right below and right above the surface, not at a distance from the surface, okay? So if I want to look at one point here, okay, what I can do is that I can choose a box that sits a little above the surface, like this, and extends to a little bit below the surface. Okay, and if I want to look at the cross section of that, I can look at this, the surface that has surface charge density, and this box, let's say with an area of A, is sitting tiny bit above the surface with area of A and tiny bit below the surface, okay? So that if we measure the electric field here, we are looking at E below. If we measure the electric field on the top, we are looking at E above, okay? So is the geometry more or less clear here, what we are looking at? Yes? Okay, very good. Okay, so now I want to remind you of the Gauss law, that for any surface, for any box, including this box that I draw here, okay, the integral of E dot dA over the whole surface means covering the top and bottom surface and sides. E dot dA should be equal to 1 over epsilon 0 Q enclosed. And that Q enclosed counts the total electric charges within the box. Has nothing to do with the electric charges outside the box, okay? Even though the electric field could have been created by the charges outside, But this integral of the flux over the closed surface is only proportional to the charge inside the box, okay? And in this case, the charge inside the box is only from the surface, because the box we chose here is very, very tiny, small, and the above and bottom sides of the box are so close to the surface of the surface charge distribution. Sounds good? Now, if we do this integral, you remember that it's a dot product. Okay, so if E above is a random field, let's say with this direction, and if E below is a field with this direction, okay, if we do this integral, the sides, left and right sides, are going to cancel out each other, because we said the box is small, so whatever we get on the right, we get the same thing on this on the side as well. Okay, and EDA, this integral, is the integral E above times A, which is the surface area, I would say. A is a scalar, so let me write A here. A times E above times n hat. N hat is a vector, unit vector in this direction. Normal to the surface, okay? I put n hat here because here we have the dot product. The magnitude of A is going to be surface area, and the dot product of E above times n times A is going to be technically dA, E dot dA integrated over the top surface, okay? And for the bottom side, I'm going to say minus A E below times n hat. I'm going to use the same n hat. That's why I put a negative sign here. Okay. If I wanted to use n hat going in the bottom direction, I would have used positive. But because I want to use both of them, for both of them, the same n hat, I use negative sign here. And that should be equal to 1 over epsilon 0 Q enclosed, which is A times sigma. Okay. A times sigma is our Q enclosed here. A is the surface area, sigma is the surface charge density, and that as a whole is going to be enclosed charge. So far, so good? Okay. So I'm going to simplify this a little bit. I'm doing the dot product of E above times n hat and the dot product of E below times n hat. And what counts is, so if I have this one as E above, if you do the dot product, what counts is only the normal component of the electric field to the surface, okay, when you do the dot product. Okay, I want to change this notation and write it more simply as E times A times E with this sign, which refers to the normal component of the electric field that is above the surface. And for the other one, I want to say A times E times the normal component of the electric field that is below the surface. And that should be equal to 1 over epsilon 0 A times sigma. Okay. And now, obviously, we can cancel out A here from the all sides. And what we get is that we see that E above, I want to rewrite this, E above minus E below. If we look at the normal component, that is equal to sigma over epsilon 0. Okay, and I'm going to put that in a box, and I'm going to discuss this a little bit. Okay, so what is the meaning of this? The second one is the electric field above the surface, only the normal component of the electric field. Okay, and the second one is the same thing, the normal component of the electric field. Was it a question?
Yeah, that was me. The little symbol at the top of the E, does that represent perpendicular?
Yes.
Okay, thank you.
Yeah, it's perpendicular, which is technically the normal component, but perpendicular or normal component of the electric field to the surface. Okay, so we have E above perpendicular minus E below perpendicular. Okay, so what we have here is technically the difference between the two. Okay, and that shows the discontinuity in the normal component of the electric field, which is going to be proportional to the sigma over epsilon zero. Okay, so if you have a strong surface charge density, you're going to see a bigger discontinuity in electric field. Okay, and if you remember, this is somewhat similar to the electric fields that we calculated above and below of a uniformly charged surface with the assumption that that surface extends to infinity, right? If you remember, earlier on when we discussed the Gauss law, one example was when we have a surface charge distribution that extends to infinity. Above this, we get an electric field which is equal to sigma over 2 epsilon 0, and below this, we get electric field which is sigma over 2 epsilon 0. Okay, the same magnitude, but the directions are exactly opposite. Okay, so if you want to cross from the bottom to above, what you will see in fact a discontinuity in electric field, which is equal to exactly this amount. Sigma over 2 epsilon 0 minus sigma over 2 epsilon 0 with opposite signs. This technically, if you add them up, it's going to be sigma over epsilon. Okay, so whenever you have surface charge density, there's going to be discontinuity in the normal component of the electric field. Okay, so how about the horizontal component or tangential component of the electric field? Do you expect any discontinuity?
Professor, can I ask a question? For the line that has the E above and below to the right, on the very right of the board.
Okay, yes.
Yeah, under the backward,
Yeah.
I forgot what it's called. It's backward 6 over, is it 2 E naught? What is that?
Sigma, sorry, this is sigma over 2 epsilon 0.
Okay, sorry. Thank you so much.
And this one is sigma over 2 epsilon 0 2. The point is that they are in opposite directions. One of the above is going up, below is going down. So that means there's a discontinuity.
Okay, thank you. Sorry.
No, that's fine. Please ask. Sounds good? Okay, so perpendicular component, normal component has discontinuity. How about tangential component? Okay, so let's discuss this as well. What is the source of discontinuity? Source of discontinuity comes from the electric field that is created right by the surface. Okay, and the surface charge density creates electric field normal to its direction. Okay, and it does not create any electric field tangential to the surface. Okay, later on you will see magnetic field. Yes, we see that, but in electric field, the surface cannot create any electric field tangential to its surface. Okay, and because of that, there will not be any discontinuity in the tangential component of the electric field. That means if you have, let's say this is E below, whatever components that the electric field has here, it will have exactly the same component if you go above the surface. Okay, and there's also a way to show that, and that is if you look at the surface, again, imagine this is the cross section. I choose a line like this. Okay, it's not a good box. I choose a path like this. Okay, and I move from here to here to here and to here. This is not a box, this is only a path here. Okay, if we do integral of E dl over this closed path, okay, what do I get? I get the tangential component of the electric field that I'm showing like this, E above, times L, considering that the distance here is L, minus, I'm continuing here, minus E below tangential component times L. These two, if you subtract, that has to be 0 because this is always 0 field for the electric field. Okay, this is based on the curl, this is always 0. So E above times L, E below times L is 0. That means E above the tangential component should be equal to E below the tangential component. Okay, sounds good. So the normal component, we have discontinuity proportional to the surface charge density. For the tangential component, there is no discontinuity, and that should be exactly similar to each other if we move from the bottom to above.
Do how you drew the red arrows on the little diagram? They go the same direction?
It has to be the same direction. The tangential component of the electric field, whatever you have below it, you will have the same above.
Okay. But they don't go opposite ever, right? They always go together no matter
They
which way.
cannot go opposite.
Okay,
It
cool.
should be exactly same direction, same magnitude.
Okay, thank you.
Okay. And there's a nicer way to combine both of these two using the vector notation. And that is, you can write E above minus E below. Okay, so this is the vector notation of whatever E we have above, okay? And that is not normal, that is not tangential. This is a combination of tangential and normal components. And then here we have E below, and that should be equal to sigma over epsilon 0 times n hat. And this is the normal vector to the surface. Okay, so this is a vector perpendicular to the surface, and this single equation in vector notation actually combines the two. And that means in perpendicular direction, we have discontinuity. In the tangential direction, there is no discontinuity because this component on the right-hand side only has the normal component. Sounds good?
Professor, for the part where E above minus E below is equal to, what was it? That sigma over epsilon naught, are the E's in that, they don't represent the perpendicular or the parallels, do they?
Which
Do they
one?
just
This is perpendicular,
Yeah.
this is parallel. This is the vector notation, which is combination of parallel and
Oh, okay, so that's just the E vector.
this
Okay.
is just E vector right above the surface.
Yeah, okay, okay, that makes sense. I was a little confused
Yeah.
by the notation.
Yeah, as I said, this is a way to combine these two and write it in a vector notation.
Got it.
Professor, you were
Yes.
saying something about the source of discontinuity earlier.
Yes,
Right, so that's because of the electric field right above the surface?
that's because of the electric field created by the surface charge. And the way electric field is created by surface charge is similar to this. If you're
Okay.
above the surface, you get a component of sigma over 2 epsilon 0 pushing up if it's positive charge. And below the surface, you get sigma over 2 epsilon 0 pushing down, okay? And this field created by the surface is a source of electric discontinuity.
Okay, thank you.
Make sense?
Yep.
Good. Any more question on this? This is an important topic, okay? It's not conceptually difficult. I mean, it's not trivial either, but it's one of those things. Once you learn it, then you know it for the rest of your life. It's one of those sort of things. So once you get it, it's gonna be easy for you. So if it's unclear or anything, it's the best time to ask question. And it also helps your peers to learn it too.
Professor,
Yes.
is it always, is the shape arbitrarily? I mean, would the problem be more complicated if instead of a square or a cube going through a charge, going into a charge density field, would it
Yes
be
and
more?
no. Okay, so let me be clear here. The shape of the surface is important in the sense that what sort of electric field it creates way above and way below the surface. Okay, but when you are, the whole discussion here is for the case of you are being so close to the surface. Okay, so E above here that we discussed, like here or here, is the electric field right above the surface. Imagine you're super, super close, but right above the surface. The same goes for E below, okay? Imagine you're just below the surface. If you're super close to the surface, then the shape doesn't really matter because whatever shape it has, you're gonna see a flat surface because you're so close to the surface, okay? So the whole discussion here is for the electric fields created in a very near distance from the surface, and that makes the whole shape irrelevant, okay? But if you want to go a little further away from the surface, then yes, the surface, the way it's created, if it's cube or a square or whatever geometrical shape, that becomes an important factor. Was it the answer to your question, hopefully?
Yeah.
Okay. Sounds good. Okay. So now going back to the case of the sphere we had, right? We said electric potential is continuous, electric field is discontinuous, and we had this discontinuity as you pass the surface of the spherical shell, okay? So hopefully now you have a better idea of where this discontinuity comes from. You have discontinuity because you had a spherical shell with uniform charge distribution, okay? Now you can imagine if it was not charge distribution on the surface, if it was not a shell, but it was a solid sphere with uniform volume charge density, okay? If that was the case, you would have continuous potential and also continuous electric field because there is no surface charge density. There is continuous distribution of the charge over the whole surface, whole volume of the sphere, okay? So I think that's a good practice for you guys to look at the electric field created by the uniform charge distribution on the surface and look at the electric field inside and outside. And then you will see right on the surface of the sphere, you have change in the shape of the electric field, but you do not have discontinuity of the electric field. Sounds good? Is it more or less clear? Any question?
Nope.
Okay. So the last piece for this discussion, we have electric field discontinuity, but potential is going to be always continuous, okay? So if you're moving from below the surface coming to here and going above, the way you calculate electric potential is you're integrating electric field, okay? Even though you have discontinuity in electric field, the electric potential will be continuous. What you will have is very similar to this. You will have discontinuity in the slope of the potential, not the potential itself. So whenever there's a surface, you're going to see a bend like this, okay, a sharp bend for electric potential, but there won't be any discontinuity in the value, okay? And remember, a slope of the potential is always related to the field, electric field. Very similar to the slope of, like in mechanics, you know, you have position as a function of time, a slope of that is velocity, right? You have that relationship in mechanics. Similar thing goes with electric potential and electric field. The slope here is with respect to the position. In mechanics, the slope is with respect to time. Okay. Sounds good? Any question? So I'm going to stop discussion on boundary conditions here. So we covered the example we had on electric potential and boundary condition. And now I'm going to move on to work and energy in electrostatics. Okay, so let me erase these things here. Okay, so we talked about charge distribution, we talked about the electric field, and we did a lot of emphasis on electric field is important, and I always refer to that. If you have electric field, you can calculate force as well. Okay, so at the end, if you remember all the discussions we had, we sort of relate everything to electric field and force. And you know, whenever there's force involved, if you want to make any change, if you want to move anything or change charge distribution, or even you want to create a collection of charge distribution, then that means you need to get some work done to make that thing happen. Okay, so what we're going to discuss here is I want to start from very basic, simple configuration of one or two and a few more electric charges, point charges, and I want to discuss what kind of energy we need to spend to bring these charges together. Okay, so I'm going to start with point charges, and I'm going to move on from point charge to continuous charge distribution, as we did for many of the discussions in this course. Okay, and from that, I want to discuss what is the force and work and energy, okay, the work and energy needed to create a specific charge distribution, either point charges or continuous charges. And from that, I want to mathematically develop a framework, and eventually I want to assign very special function that defines the density of energy in an electric field. Okay, so the discussion is going to end like this. I'm going to tell you that if you have certain charges that create certain electric field, the way you can look at the energy of this electric field is whenever you have electric field, wherever you have electric field, you can assume there is an energy associated with that electric field in a space. Okay, and if you integrate that energy over the whole space, that's going to tell you how much work was done to create that electric charge distribution, which created the electric field. Okay, so this is the overall picture. Let's start from the simple case, and then we build up on that. Okay, so it's 10:30. I'm not sure if I can finish the discussion here, but it's a good time to start it, and we continue this on Thursday. Okay, so here is the way I want you guys to think about this. Imagine you bring a charge Q1 to one point in a space, okay? And as you imagine this, imagine the whole world is empty vacuum, nothing else, okay? We just bring one charge Q from all the way from infinity to this point, okay? Because there is nothing else in a space, what happens is that bringing this charge from infinity to here doesn't cost us energy, okay? Because there's no other particle in the universe to push this in any direction, okay? I just bring this one very happily and put it right here at this point, okay? And once I put this here, it creates the electric field and electric potential in the space, okay? The next part is bringing a second charge, okay? Imagine I bring Q2, okay? Again, very similar. I bring that from infinity to this point, okay? And if Q1 sitting at position R1, I would say Q2 is sitting now at position R2, okay? Now the difference is that when I'm bringing R2 from infinity to here, it's not free anymore. I need to do some work to bring it here because all the way from infinity to this point, Q2 is interacting with Q1. If let's say they are both positively charged, they are repelling each other. So I need to get some work done to bring it here, okay? So bringing Q2 here will cost me some energy and work, okay? So now the way we calculate energy is very simple. We're gonna go back to mechanics. The work done is always the integral of force times dl, moving from one point A to one point B. Okay, so going from A to B, the integral of f dl is gonna tell me how much work I need to get the work to do this thing done. Okay, this is very basic mechanics. The same thing goes here. And now in electrostatics, what we have is that we have the force defined as Q times electric field. So what I integrate is Q times E that dl. And this is the Q, capital Q is the electric field of my test charge. So in this case, it's going to be Q2, okay? And if I expand this, because Q, the electric charge does not change value over the course of this motion, I can take that out of the integral and write it in terms of the integral of E dot dl from A to B. Okay, so this is the work, okay? So now if you guys look at this, this has very familiar form. Okay, so this is the definition of electric potential. Okay, E that dl is the electric potential is negative of the electric potential at B. So something like this, minus VB minus VA. Sounds good? So the work done over this course is Q times negative of VB plus VA. Okay. So this is the work done by which force? By electrostatic force, which is Q times E. Okay. So if I want to calculate the work that I need to do to bring this charge all the way here, I should look at the negative of the force because my force is gonna counteract the force of the electrostatic interaction between these two. Okay. So this is work of the electrostatic field. Okay, and the work that I need to do to move this, I'm going to say W mi, that's going to be Q times VB minus VA, which is negative of the other one. Okay, now imagine you bring the particle from infinity to this point. Okay, so the VA here is going to be V of infinity, right? And a lot of time, especially when we have localized charge distribution V infinity, we assume that is being zero, okay? So the work needed to bring the second charge from infinity to this point is going to be Q times VR. I'm changing B to R, meaning that I'm looking at the electric potential right at the final position of the charge. Okay, so this is Q times VR, and that is technically the electric field that the electric potential that we have at the final position. So the electric charge of the particle times electric potential at the final position of the particle is going to tell me how much work I need to do to make this transition happen. Okay, so if I want to continue this situation following this, I would say bringing the charge number 2, I'm going to say W2 to this point is Q2 times potential created by charge number 1 at the position R2. And the simple way of writing that is 1 over 4 pi epsilon 0, because we know that the potential created by Q1 is 1 over 4 pi epsilon 0, Q1 over R. So this is going to be 1 over 4 pi epsilon 0 Q1 Q2 divided by R12. And R12 is the distance vector from number 1 to number 2. Okay, so the work needed to bring particle number 2 is 1 over 4 pi epsilon 0 Q1, charge of the first one, Q2, charge of the second one, divided by R12, which is a separation distance between 1 and 2, at the final position when they settle. Sounds good? Is this clear so far? Okay, so now, if it's clear, I'm going to bring another charge as well. I'm going to put charge Q3 at this point as well. That sits at a distance of R13 from the first one and at a distance of R23 from the second one. Okay, so I have now the third charge sitting here. What is the work needed to bring the number 3? The thing is that when we are bringing number 3, we are interacting with 2 other charges, not 1 more. Okay, so we're going to have 2 terms like this. Q3 interacting with number 1 and Q3 interacting with number 2. Okay, so the total work is going to be 1 over 4 pi epsilon 0 times Q1, Q3, R13 plus 1 over 4 pi epsilon 0 Q1, Q2, Q3 over R1, R2, 3. Sounds good? So we have 2 terms when we bring number 3. If we bring a number 4, that number 4 is interacting with 3 more particles. Okay, so we're going to have very similar terms. We're going to have Q4, Q1, R14. We're going to have Q4, Q2, Q4, Q3, and so on. Okay, so if you bring particle number n, that particle is interacting with n minus 1 particle that has already been sitting here. Okay, so if you want to calculate the total work needed to bring all these things together, we need to add up these ones together. The work of W2, the work of W3, the work of W4, and so on. Okay, if we look at the total work, let's look at this work for 3 of these chart distributions, and I'm going to say work total. Okay, I'm going to pull out the 1 over 4 pi epsilon 0 factor. So I'm going to write this like this. And then what I have here is Q1, Q2, R12. I have Q1, Q3, R13, and then I have Q2, Q3, R23. Okay, something like this. And then if I had more particles, I had more terms like this. Okay, mathematically, there's a way to include all these additions and all charges in terms of sigmas. Okay, and the way the sigma looks like is this. If you look at this, what we are doing is that we are adding all these pairwise interactions. So the total work, if we bring n particles together, it's 1 over 4 pi epsilon 0. We have a sigma of starting from 1 all the way to n, assuming that we have n particles. We have another sigma of j, okay, starting from values of j greater than I. I'm going to tell you a little bit what I chose, why we chose like this, all the way to n. and then we have Qi, Qj over R, I, J. And that is, this summation is going to include all these contributions. Okay, so if you have this sigma, you're calculating everything. Why did I choose J greater than I and not J starting from I? Because if I start from 1, what I'm doing is that I'm double counting the contributions. If I start from 1, I will be counting Q2, Q3, and also Q3, Q2. So I'm counting one of these terms, not once, but twice. Okay, to avoid that, what I did was I said in the second summation, J should be definitely greater than I. Okay, but having a summation like this makes things difficult. Another way, which is mathematically easier, is intentionally starting this from 1 and do counting everything twice. And then divide everything by 2 in order to scale it back to what it should be. Okay, so this summation, another way, which turns out to be nicer, is writing 1 over, instead of 4, I'm going to write 8. I'm going to do that red so that you can see what is changing here. 8 pi epsilon 0 sigma of I from 1 to n, and j from 1 to n as well. And then I do qi, qj over rij. So here I know if I start from 1, I'm double counting, but I here use 8 instead of 4 to scale it back to what it should be. Okay, there's one thing that we need to be careful, that j can be any value from 1 to n, except j cannot be equal to I. Okay, because we are looking at the pairwise interaction. We are not looking at Q2, Q2 or Q1, Q1. We are looking at Q1, Q3, Q2, Q3, and all these pairwise interactions. So here I'm going to note that j should not be equal to I. Sounds good? Okay. So one more trick to make it look more simple. If you look at the second summation, this is over j. So if you are doing the second summation, I is a constant. That means qi is a constant. So you can pull qi out of the second summation and write it as sigma w total is 1 over 8 pi epsilon 0 sigma over I from 1 to n qi, and then sigma over j not being equal to I from 1 to n as well, qj divided by rij. Okay, so if you look at this, this has the shape of electric potential combined with this. Okay, so if I want to rearrange this a little bit, I'm going to write this W total is, I keep 1 over 2 here, and I do sigma over qi, I from 1 to n, and I do, in parentheses, 1 over 4 pi epsilon 0, sigma over j not being equal to I all the way to n, qj over rij. Okay. And if you look at this parentheses here, this is exactly the potential, the electric potential created by all other charges at the position of the qi. Okay. And this can be written very simply, electric potential at the position of Ri, created by all charges except the charge sitting at the position I. Okay, so I'm going to stop here. Okay, I'm going to stop here. This is very interesting. We are moving in a very interesting direction. On Thursday, I'm going to technically start from here, quickly jump to here, and tell you what it means, this summation of qi times vi, because that is exactly the kind of electric energy we can we can assign to any charge in discrete charge distribution and move on from here to continuous charge distribution and so on. Okay, so maybe we can take one or two questions on this before finishing the session, if you have.
Yeah, why divide by 1/2 to get 1/8?
Okay, because here I said J needs to be greater than 1 so that we avoid double counting the contributions. Okay, so all these terms, see you have, let's say, Q1 times Q3. You don't want to add Q3 times Q1 as well, because that's going to be exactly the same contribution. We don't want to count twice. Because of that, we use J being greater than I. Okay, but doing this sort of summation is difficult. Another alternative is starting from J equal to 1 and including everything with intentionally and knowing the fact that we are double counting. So what we are doing in these summations, we are doing double counting, but then we divide by 2 so that we scale it back to actual value it should be.
Oh, so it's basically the same thing on 1/4 pi e epsilon, but now you're counting the other factor of.
Yes, yes. So I'm double counting here and then dividing by 2 here so that we get the exact same thing we want. Sounds good?
Professor?
Yes.
So, so since we did the half to account for double counting, like to me logically, like for if we put J is not equal to I, aren't we doing that again, or is that different
No.
from?
If we put J equal to I, we're gonna have unmeaningful terms. We're gonna have like Q1 divided by 0. We just do not have any term like that. Okay, so including J not equal to I, we are still double counting.
Okay.
Sounds good? I'm gonna recap this on Thursday as well. Okay, we are out of time. Okay, and I know some students have class at 11 as well. So let's stop here, and I will see you guys back on Thursday morning. Okay.
Thank you, Professor.
Thanks,
Okay.
Professor.
Professor.
Okay, you guys enjoy the rest of your day.